Hi everyone, this is question 7 on page 93, Fundamental Applied Mathematics. So we've got a wedge this time with 2 weights on it, which is a little bit different, but it's nothing that we can't handle. 2 45-degree angles will make the trig a little bit easier, and 2 particles of mass 2m and n. So as usual, we're going to start off drawing our force diagrams, and we'll do 2 separate diagrams, one for the particles and one for the wedge. Okay, so here are my diagrams. I'm going to start off just with the particles. Sorry, I should include an A there as well. For the particles, you've got 2mg acting downwards. It's going to have to be resolved into components perpendicular to this surface and parallel to this surface. So you get 2mg cos, and that's a 45-degree angle there, cos 45, and 2mg sine 45 here. And this you also resolve the same way. I'm going to resolve it this way, show parallel and perpendicular, just so that I have space. There's my 45-degree angle. You get mg acting downwards, and that's the adjacent side, so mg cos 45, and this is the opposite, mg sine 45 degrees. And the accelerations, now you've got separate accelerations. I'm going to call this one P and this one Q, and oh, I shouldn't have, well, yeah, and then this acceleration here, A, has to be resolved into components that are parallel to this surface and perpendicular to this surface. Now we don't need to resolve twice, which you would have to do if these were 2 different angles. You'd have to resolve this. Let's suppose that was 30 and 60. Once with the 30-degree angle here, and then you'd have to resolve it again for the 60-degree angle. Okay, but we don't, because it's 45 and 45. So what do we get? We get, that's A sine 45, and this component here is A cos 45. Okay, so it's already quite a busy diagram. Coming over here, we haven't even looked, excuse me, at our normal forces, which are acting that way. I'm going to call that actually R1. I'm going to call this R2. Okay, and after the fiasco in the last video, let me just double check that we've no friction. Smooth, all of whose faces are smooth, rests on a horizontal table. Doesn't say anything about friction, okay, even though it doesn't actually say the table is smooth either. So we no friction to worry about. If we come over here, what the particle is, or sorry, what the wedge is experiencing is R2 acting inwards and R1 acting inwards. So both of those need to be resolved into components perpendicular to the ground and parallel to the ground. Okay, again, 45, very easy. That's going to be R2 sine 45. And that's going to be R2 cos 45. And here, parallel and perpendicular. The perpendicular component is going to be R1, that's 45 there. So R1 cos 45. And this component is R1 sine 45. Okay, so we have 5 simultaneous equations here, potentially 6, but I think we only need 5, 2 for each particle and 2 for the wedge, even though unless we're looking at friction, we never really worry too much about perpendicular to the ground. So horizontal to the ground is what we're interested in, or parallel to the ground. So let's say particle 1 is the mass 2m particle. Our parallel equation is going to say, well, the force acting is 2mg sine 45. Now, sine 45 and cos 45, you can write them as 1 over root 2 or root 2 over 2. That's the same number. I'm going to work with this one. So we are going to get here, the force acting downwards is 2mg times root 2 over 2. Okay, that's the force acting down. There's no force acting anywhere else. Minus, sorry, is equal to, the mass is 2m times the acceleration is p minus the acceleration caused by the moving wedge, which is A cos 45, so root 2 over 2. Okay, perpendicular to that surface the forces acting are 2mg cos 45 and R2. So we get 2mg cos 45 is root 2 over 2 minus, in the opposite direction, R2 equals, its mass is still 2m, and its acceleration now in that direction is a sine 45. And sine 45, root 2 over 2. Right, that's for the 2m particle. For the m particle, our parallel to the surface is mg cos 45. So mg times 2 over root 2 minus, no other forces, equals, its mass is just m, and its acceleration here is, it's q plus, in the same direction, that a sine 45. Okay, so mind your signs there. It'd be easy enough to make an error there, but those are in the same direction. It's being pushed, because we're told the wedge moves to the right. It's being pushed by the fact of the wedge, and it's sliding down under its own bat. Okay, that's root 2 over 2. Sorry about that. Perpendicular, you're going to have mg sine 45. It's the only force acting. Oh, excuse me. No, it's not. That's acting into the wedge. R1 minus R1 is acting out of the wedge. Okay. So in and out equals, mass is still m, times acceleration this time is a cos 45 is the only acceleration. It's in the same direction as R1, so minus a cos 45. Okay, and cos 45 is root 2 over 2. I could have done that here as well. That's root 2 over 2. Okay, and then the last equation, that's 4 of them, is from the particle up here to the right, you get R2 sine 45. To the left, you get R1 sine 45, and you get an acceleration of a. So that is, to the right is positive, so R2 sine 45, root 2 over 2, minus R1 sine 45, root 2 over 2 again, equals 3m times the acceleration is just a. Okay, so let's tidy that up a little bit by multiplying through by 2. You get root 2 R2 minus root 2 R1 equals 6ma. Okay, so we've got 5 equations here. I'm just going to tidy them up, put them on the next page to show you where to go next. In fact, even before I do tidy up, I'll just point out that there's 2's cancel here. So that's really just mg root 2. 2's cancel here, that's mg root 2 minus R2. 2's cancel here. Okay, and here that becomes 2np minus, and 2's cancel. You get ma root 2. Okay, so just before I go rewriting them, that's the cancelling that I'm doing. And actually over here, I'm not able to cancel, but I'm going to multiply through by 2. Excuse me. I'm going to multiply through by 2 as I, as I rewrite these. Okay, so here's my 5 equations. So just to point out, what we're looking for is the acceleration of the wedge, which is a. You have it here in terms of R1 and R2. So you can get R1 out of this equation here, which, by the way, I've multiplied through by 2 to get these. And you can get R2 out of this equation here. Okay, so you can actually disregard these equations for this question because they're not asking you how the particles move at all. So for this one, we get mg root 2 minus ma root 2 equals R2. And for this one, moving this over and this over, you get mg root 2 plus ma root 2 equals 2R1. And I guess you could divide through there if you want to. I'm actually not going to, because what I'm going to do here is I'm going to multiply this by root 2. So I get 2R2 minus 2R1 equals 6 root 2 ma. Okay, because now I can substitute these in here. 2R2 becomes 2 times this minus 2R1 is what we have here equals 6 root 2 MA. Okay, so 2 times R2 is 2 times mg root 2 minus ma root 2 minus R1, 2 times R1 is mg root 2 plus ma root 2 equals 6 root 2 ma. So look, you've got a is the only variable there. M's are about to cancel, lowercase g we know. So what do we get? Everything has a root 2 in it as well. Let's tidy this up a little bit before we go canceling. 2 mg root 2 minus 2 ma root 2 minus mg root 2 minus ma root 2 equals 6 root 2 ma. Okay, so m's cancel because every term contains an m, and root 2's cancel because every term contains a root 2. And you get yourself 2g minus 2a minus g minus a equals 6a. Tidy that up over here. 2g take away g, that's g minus 3a equals 6a. G is 9a, and our acceleration here is g over 9. And that's what they've asked us for. So there you go. That's question 7, page 93.